like to call now Matthew Coverdale. He's a satellite analyst. Mauro, you raising your hand again? Okay. Matthew is a satellite analyst from NOAA, and he will give his presentation now. Matthew, can you share your slide and open your mic, please?
Yes. Saying I'm not a presenter right now.
Okay. Try now.
Yep, there we go. Okay, can everybody see my screen?
Yes.
Okay, great. Thank you, Karen. Good afternoon, everybody. I'm Matthew Coverdale. I'm a satellite analyst at NOAA's Satellite Analysis Branch, like Karen said. And I'm just going to give you a really quick kind of talk on NOAA's satellite analysis program for oil spills, and then also our sort of regional COSTA initiative that we've been kind of spinning up the past year or so. So with the oil industry that we have, there are going to be associated risks with that that can have adverse effects on tourism, the industry itself, ecosystems. This example on the top left is from Mauritius. That was an oil spill back a couple of years ago, and it actually spilled oil straight onto a coral reef, having a adverse effect on that ecosystem. In the top right, this is the BP Deepwater Horizon oil spill in 2010 in the Gulf of Mexico. And then also storm damage. Hurricane Dorian in 2019 actually blew the tops off these oil storage tanks. Luckily, a lot of it didn't get into the ocean there, but it still affected the land there. And then obviously marine wildlife will be impacted anytime there's an oil spill. So like I said, there's going to be inherent risk whenever you have an oil or illegal bilge dumping from ships and storms. There's going to be oil spills. Some notable ones that we have had a big part in, or small part in, have been right after our program started, 2014 oil spill in Trinidad and Tobago. Like Paulo showed, the mysterious spill off the Brazilian coast in 2019, which we also supported, the Mauritius spill that I showed you in the last slide. And then more recently, we supported a Sri Lanka chemical and oil spill in 2021. And then the most recent one, or one of the more recent ones, was January 2022 Peru oil spill. And that one was actually caused in part by a tsunami, which was caused by the volcanic eruption in the South Pacific in January. So it's a lot of different things can come together to create an oil spill. And again, with all the high density of ship traffic in and around our waters, accidental and intentional spills from ships do happen. So satellite monitoring has been a proven, timely, and cost-effective way to monitor oil spills. We use a largely free source data. We do have a couple commercial images that we pay for here and there, but mainly it's all free source data. We use optical imagery and synthetic aperture radar or STAR imagery. Obviously for optical, it's like a true color image. You're going to need it to be daytime, and to see the ocean, you're going to need it to be cloud free. But then when synthetic aperture radar data, you can use it 24/7. Doesn't matter if it's day or night. And the sensor can cut straight through the clouds to image the surface of the ocean. Mainly what we use for optical is going to be Landsat 8 and 9. and then Sentinel-2. And to a lesser extent, sometimes Aster, which is a NASA satellite, and MODIS, which also is. And then for SAR imagery, we mainly use Sentinel-1 imagery, which is from ESA, along with Sentinel-2. So just going back a little bit to the start of the satellite analysis branch's oil spill pollution program. It started in 2009 and is a 24/7 analyst-driven satellite marine pollution program. And we are dedicated to monitoring for marine oil spills typically. The program, like I said, analyzes mostly free satellite imagery for accidental and intentional oil discharges. And we also create what we call a marine pollution surveillance report, which when we send out notifies federal and state agencies, including the Coast Guard and oil facility inspectors. So once, as you can see in the bottom in the pictures, if we send something out in the morning, the Coast Guard can still have time to go do an overflight in the Gulf of Mexico that same day. So it's very timely in that way. The area of responsibility we look over, like I said, it's just the U.S. exclusive economic zone. The northern Gulf of Mexico is part of that, the East Coast, the Pacific Coast. The waters around Alaska, and then it's not pictured here, but also the waters around Hawaii and Guam. So yeah, like I said, there's accidental discharges that create oil spills, big or small, Deepwater Horizon in the Gulf, just an equipment failure, a little pinhole leak in a pipeline, and then any disaster, hurricane, something like that, or a shipwreck. We have some shipwrecks in the Gulf along the East Coast, some from back in the World War II era that still leak oil to this day. So those are just some examples of accidental discharges that will happen. And then there's also the intentional, which also we are definitely trying to mitigate for. So that largely comes in the way of bilge jumping from ships instead of paying to properly dispose of it. And that is a MARPOL violation as well. So when we're looking at the satellite data, it helps if we have some other additional data to kind of help us with what we're looking at. So we'll have like layers, like a platform layer, like you see in the bottom left, that just highlights all the oil platforms that we have in the Gulf of Mexico. We have the same sort of thing for pipelines throughout the Gulf of Mexico, wellheads, boreholes. We also have a natural seeps layer because the Gulf of Mexico has a lot of natural oil seeps. And just like Paulo said, we're not really concerned about those. What we really want to get the Coast Guard's attention to is the man-made oil spills. And then the shipwreck locations as well. Those will help. And then also ocean currents and surface winds. That can help kind of give you a short-term guess as to what might happen right immediately after in the hours following. But yeah, I'm not an oil spill modeler, so we really don't use it for that. But winds can come in really handy, especially when you're using SAR data, because if you have an area that's like washed out in the SAR data, it looks a little too bright, you can cross-reference that with the winds and say, I guess it looks like the winds were a little 15 knot winds, because then if you have calm winds, you'll get a big area of just darkness where you can't really see anything. So it helps to kind of rule out a big dark areas, weak winds, if you're having trouble deciphering that. So here is an example of one of our MPSRs. This one's using optical imagery. And as you can see, you can really kind of tell some of the colors in this one. One thing about optical imagery is that because it's a true color RGB and we can decipher colors and stuff like that, we can pick out some relatively thicker oil sometimes. Here you can see that the grayer metallic to white color that's surrounded by this other one is probably a little bit thicker. So that is helpful with the optical imagery. That's something we don't really have the capability of to do with SAR imagery. It's criteria up in the top. Then if you go down the side, report time and date, the data source the satellite came from, resolution, the size of the spill, the area, and then also we also write up some remarks as well, and then list any uncertainties we might have. But as you can see, this one was a high confidence. So, and then here's an example of a SAR MPSR. This was the bilge dumping, as you can see, with the segmented anomalies that we found. But yeah, here you can see it's oil will always come back darker because of the smoothing effect. So yeah, just a little different, but very useful. So now moving on to COSTA. And COSTA is the collaboration for oil satellite tracking in the Americas. It's really a regional network of oil spill monitoring that we're trying to get going of oil spills. The first country that we trained was Trinidad and Tobago back last summer, and they have been fully operational since July 2021. Right now, they just look at their EEZ, but they do have plans to expand further into the Caribbean in the future. And then this last summer, just a few months ago, we finished training Mexico and Peru to analyze their EEZs. And they're currently transitioning to operations, but the training has been completed. And then we also have some Central American countries that have shown interest, and Colombia. So we're thinking about maybe trying to start that training in the coming months and probably in the spring. And then here are all the partners' logos on the right side. So since we started COSTA, there have been a couple notable events that we, as a group international effort, have kind of worked together on. In August 2021 in Trinidad and Tobago, just a month after they went operational with their program, Trinidad and Tobago had a pipeline oil spill. They fully executed and helped out the response on the ground there a lot to kind of just let authorities know exactly where the oil is. So they really showed how it could be beneficial for them down there. And any time that there is a international or a spill with the COSTA nation, we all kind of support. The first report that Trinidad and Tobago sent out, this was from very early on the 10th of August. And then if we step forward, this was later on the 10th of August. And then the 11th. And then finally on the 13th. And you can see just how much oil and how much it has drifted. So yeah, they did a really good job with that. Another notable spill happened back in May 2022. So what was interesting about this one, this was an oil tanker near Jamaica that sank. So what happened was COSTA satellite imagery support from IMA in Trinidad and Tobago was requested on June 3rd. And once they got that request, between June 3rd and June 8th, IMA in Trinidad and Tobago were able to create 3 reports. And then by the time NOAA, we got formal requests to support this was June 8th. And by that point, all the oil was gone once we started looking. But luckily, Trinidad and Tobago had the program up and running, so they saw it once they got requests, and they were able to send out a few reports. If it had waited till it got all the way to us, like I said, we wouldn't have seen anything, or at least not maybe retroactively, but nothing that could help support in real time. So cutting the response by 5 days was really beneficial for them down there. And then just to summarize things, satellite imagery is a powerful tool that we use to help track marine spills and aid in oil spill response. And NOAA's satellite analysis branch is a totally analyst-driven oil spill monitoring program. And like I said, we use mostly free images. And then COSTA aims to form a regional alliance to train and establish a near real-time satellite oil spill monitoring and analysis network in the Americas region. And yeah, like I said, so far 3 countries have been trained and 1 country has set up a operational program that's very close to what we have here in NOAA. But yeah, that's about it. If you have any questions, please feel free to email me. My email is right there at the bottom, matthew.coverdale@noaa.gov. Or my colleague, Bonnie Zhu. Either one of us, if you have any questions. So yeah, if anybody has any questions.
Thank you, Matthew. That was great. Great presentation.
Thank you.
Yeah, I would like to call on questions, and I have a question myself before people warm up. Do you also assist in the sample analysis to see what is the oil signature for the sample when it's possible to even capture the samples, or you do the imagery assistance?
We just really handle the imagery and are just really trained to pick out oil from false positives and stuff like that in imagery. We do have partners that do look at the spectral analysis and things like that to kind of, but that's more on the research side. We're more on the operational side right now, but we're definitely interested in research topics becoming operational at some point. But yeah, that's not something we in the branch normally do, I guess.
I see. So that wouldn't be part of a project. Okay, that's very interesting.
Yeah.
Yeah, because one thing I realized when we have here around 20 projects now on oil spill other than the system is that another challenge is to, after you get the samples, is actually to run the analysis and have a good bank of samples so you can actually really identify the signature. And not always private companies are willing to help and to share their banks of information on their oil signature. And it's hard to do the forensics afterwards. So that's a challenge that also maybe we could strengthen with international cooperation also beyond the imagery. But I'll leave it here to the experts. Anyone else would like to ask any questions or comments? Okay. Great, thank you, Matthew. Let's move on to the program.
Thank you.
And now I'd like to call Robert Hallberg. He's a sonographer and a head from the Ocean Group in Geophysical Fluid Dynamics Laboratory at NOAA. So let me give you the sharing permission, Robert.
Okay.
Oh, you have it already, yeah.
I believe I am successfully sharing.
Yes.
Great. Thank you, everybody. It's a great pleasure to be able to present a little bit about what we're doing. I'm stepping back a little bit from the kind of the day-to-day aspects of monitoring, detecting, and dealing with oil spills to talk a little bit about some of the underlying technology and the community efforts that have gone into developing it, that underpins some of the things. In particular, the work that Paulo talked about is based on the MOM6 ocean model that I'm going to be describing today, and that's a broad collaboration across numerous institutions from around the world. And then I'm going to draw on some lessons from a rather unusual oil spill event, the Deepwater Horizon event back in 2010, to illustrate how these underlying capabilities can be mobilized in extreme situations. I'm having trouble. There we go. So the MOM6 ocean model is a community-based ocean model, originally developed at GFDL, but now supported by a broad community of institutions, mostly from the US, but with several major contributions from around the world, with a focus on global climate. So our emphasis here is on things like conservation properties, our ability to run in extreme environments or unusual parts of parameter space, and in particular, to be able to run for very long timescales. In particular, it's based on the idea of using vertical remapping to adapt your vertical coordinate to the what's appropriate for the particular problem that you're looking at. And this has led to its widespread adoption for a wide variety of different problems. But importantly, it's not just the adoption, but it's also the people using MOM6 have a very inviting pathway for contributing what they're doing back to the community, so that we're all working together, along with robust testing to make sure that those contributions can be done without doing anything that could endanger the use of the model by other people through unforeseen contributions. And in particular, one of the things that's notable about MOM6 is that it uses an approach to the time stepping that's able to separate out different timescales. The fastest, the external gravity waves, the internal motions are stepped on shorter timescales compared to the tracers. And for the purposes of Earth system modeling or oil spill modeling, those tracers can be stepped with much longer time steps than you would use for the dynamics. The dynamics time steps are something that has to get shorter with the resolution. The tracer time steps do not. And so whereas older versions of MOM, you might have about 20% of the cost of the physical model for each additional tracer you added on. That's a much smaller fraction, maybe about 2% in MOM6. And as you go to yet higher resolutions, that fraction becomes smaller, which opens up the possibility to affordably run with complicated Earth system models, as we'll hear about tomorrow, or rich sets of oil tracer-like dyes to help backtrack or understand what's going on, as I'll be describing in a few moments. Now, MOM6 has a number of important applications worldwide. It's being used for academic purposes by students for idealized process studies. It's at the heart of GFDL's CM4 coupled climate model. It will be used for NCAR heterogeneity in our climate systems. And similarly, there's an Australian consortium that is developing the next generation of Australian coupled climate models and operational coastal models that will be using MOM6. And within the US, there's a kind of a broad consensus for these structured mesh models to migrate towards this one common community model, so we're able to share our capabilities between groups. Importantly, we're importing a lot of the capabilities that are currently in the HICOM ocean model into MOM6, and the plan is that you'll be able to get the same capabilities with this one common MOM6 code base. Now, of these applications, one that's particularly notable, and I believe that Paulo is probably using exactly the same ocean component. This is the quarter-degree ocean model that was developed for GFDL's CM4 coupled climate model. This is now being adopted for use in NOAA's new unified forecast system for its global seasonal forecasts. So the big difference between the two is that the climate model is run in a free running mode. They're able to run a handful of ensemble members independently. For the operational forecast system, there are going to be an ensemble of these members using data assimilation, and those will be run out to timescales of months to a year or two, using exactly the same model that's able to represent a lot of the smaller scale and eddying processes in the tropics. But we are moving ahead with yet finer resolutions. The picture on the bottom left shows the resolutions that you would need in order to admit the first mode of baroclinic instability, a typical length scale associated with ocean motions. And so, whereas in the tropics, those eddy scales are relatively large, we can do pretty well with maybe not quite such a high resolution model. As you go to higher resolutions, you're able to expand the range of the ocean where you're admitting the dynamics. And so this quarter degree model is the basis for a whole hierarchy of higher resolution models, including the eighth of a degree model that you see in the bottom right, which is performing as a climate model slightly better than the quarter degree model for certain broad metrics, much better for eddy characteristics, but at the cost of obviously being a much more expensive model to run. Doubling the resolution basically increases the cost by a factor of roughly 8. Now, all of this is in the context of kind of general ocean modeling. When it comes to to oil spills, I think it's worth noting, and I think we've seen 2 presentations already today that really highlight this. For kind of the sorts of oil spills that happen routinely, there's a really good system in place for trying to identify what's happening, where it came from, where it'll go, how to respond. And in particular, the Office of Response and Restorations, NOAA's GNOME suite for ocean spill modeling that Paulo was illustrating earlier, is really well suited for kind of typical events. However, every so often, there are enormous oil spills. The most recent being the Deepwater Horizon in 2010. There was another huge blowout in the Gulf of Mexico with Ixtoc 1 in 1979. And these were events that were so big, that lasted so long, and had such large-scale impacts that this typical modeling suite was kind of out of its depth, if you will. It was beyond what it could regularly handle, because we're looking at not just the first few hours, but rather we're looking at what would happen on timescales of weeks to months to years. And so in the wake of the 2010 Deepwater Horizon, those of us doing climate modeling at GFDL were called in to use one of our prototype high-resolution ocean models to try to understand what was likely to happen in the subsequent months. Now, we did this in real time while the oil spill was going on, trying to develop the capabilities, get them validated, approved, and the message out there. And in particular, what's notable on these longer timescales is that the weathering and the microbial decay of the oil is something that will limit the spread, and was not being appropriately taken into account by some, at the time, rather alarmist concerns about this Gulf of Mexico oil spill, for instance, spreading up the east coast of the US and heading off to Europe. And so in the absence of appropriate capabilities for really constraining what was really going to happen and appropriately targeting the resources, there was a lot of chaos and confusion. At the same time, though, there was an awful lot of concern, because not all of the oil that was known to be leaking from the wellhead was actually appearing at the surface. And a lot of what was coming out was not oil, but natural gas, methane and related gases, both of which would be dissolved in the water. And so there was a lot of concern about what was happening well below the surface, which could not be directly observed from satellites. And so at the time, we were basically saying we didn't really know exactly where it was going on. We had some preliminary observations. And so using a series of different simulations where we released the oil at different depths, we were able to say something about where it would go. We knew something about the temperature dependence of the decay of oil. As was noted before, there are natural oil seeps in the Gulf of Mexico, and there are natural methanivores. There are bacteria that consume methane and some forms of oil. That's how they get their energy. And they would contribute to a reduction in the oil in the water, but they do so by consuming oxygen. And so one of the big concerns was how to handle the rates of decay of oil in the water in a plausible way. And we were able to do that with a quick survey of the literature. Subsequently, we've developed kind of a biological model which would actually envision the growth of the methanivores and the other bacteria, thinking of it more of as an Earth system process. But we were able to kind of show that with this colder water, that the oil decays much more slowly. However, the Gulf of Mexico currents at depth are much weaker. And so the oil was still very much confined relatively close to the source as a way of kind of understanding that. But as that oil decays, there's a drawdown in the oxygen deep in the water column. And this growing hypoxia was another source of potential concern, quite apart from the direct toxicity of the oil in the water itself. And as we were able to observe, there were very large plumes of methane, seen here on the bottom, being released. They were forming plumes that were kind of staying in the water column at about 1 kilometer depth. And that methane, by being an additional source of fuel for biology to consume with the oxygen, turned out to be one of the larger contributors to the oxygen drawdown. So I think it's worth kind of reflecting on this whole process. Here we are, we're 12 years later, and I think we're in much better shape to respond should something like this happen again. If you look at the timeline here, between the time of the original incident and the realization that this was going to be an event of really historic proportions, maybe a few days or a week or so later, we were finally called in to help about 3 weeks in, when it was clear that this was well beyond the scope of anything that the existing tools were available for to address. And we were able to provide some useful advice. But then we were able to get in contact with folks from the Office of Response and Restoration, and they carved out a few minutes out of their very busy schedule at the time to give us some guidance on what was likely to happen. And so over the course of this oil spill, even while the oil was still flowing at very high rates, we were able to submit a white paper to NOAA, kind of summarizing our findings, the concerns about the oxygen drawdown, our estimates of the extent of the oil, which directly addressed the concerns about oil spreading into the Atlantic and well beyond the Gulf of Mexico, which may have helped a little bit to focus the resources where they were actually needed. But even while the oil was still flowing into the water, we were able to submit a paper describing some of the longer term consequences that would be of concern based on the models, which were then of some use in helping to guide what observations we might want to be taking to really understand observationally what was happening. So this was all done in an emergency. We went from having essentially a global ocean model to one where we could apply some tracers, use it to say some useful things. If we were doing this today, we would be doing this with the operational system, so it would have this same higher resolution ocean perhaps available, but with data assimilation so that we could have something that's well vetted by being routinely used for operational forecasting. We have the modules available for oil sources, for understanding the oxygen decay, and so on. And so rather than having something which would take weeks before we even started, this is something where I suspect within about the first week, we would be able to start ramping up when there's the kind of call saying, we know there's a problem. And by maybe the second week, we would be able to say something. Importantly, because it would be based on peer-reviewed publications, as in this case, it was something that the government would be willing to publicly release. They were very reticent with that initial white paper, especially given all of the concern in the press about various stories that were coming out and information about what was the actual volume of oil and concerns. The fact that it would be publicly peer-reviewed and available would mean that it was available to help provide useful guidance for decision makers and for addressing appropriately the concerns of the general public in real time, even in the face of a very large, in this case, almost unprecedented event. Now, the oxygen drawdown that was coming out of the model was in fact something that was observed in specific profiles. You can see here the red profile shows this clear drawdown of oil at the same depth as the enhanced fluorescence associated with this plume. But curiously, because of all the things that were going on at the wellhead, where they put a cap on and take it off and chop it and this and that, there ended up being a whole bunch of different plumes that were spread out through the whole water column. And so this kind of convoluted history of the well meant that the oxygen drawdown was distributed very broadly, and it didn't get too acute at any one location. You can see here in the blue is all the profiles from dissolved oxygen. The lines going off to the left are individual plumes from individual observations, and you can see that they're very widely distributed in depth relative to the ambient conditions shown with the green line with the red hatches. So it also helps to explain why the oxygen drawdown, the acute oxygen drawdown we thought might happen at a particular depth, didn't in fact play out. It also can be used to illustrate the importance of the exact details of the ocean circulation at the time of the event. Had the loop current eddy been in a different position, it would have perhaps led to rather different consequences. Although in this case, I'm illustrating it without that microbial decay to kind of help illustrate it, it still would have had a very large impact difference on which portions of the Gulf were impacted at the time. And so the thing about this is this whole episode took place over the course of about 3 months, and we were able to get some useful key findings from this paper out in real time, even as that oil spill was going on. Had that happened today, we would be much better prepared with assimilative models, with waves coupled in, with atmospheric forecasts built in, and so on, to be able to respond much more quickly than we could at the time. Now, that was done with the global model. One of the things you're going to hear about tomorrow is some work that's going on using regional models to try to put in higher resolutions to be able to address ecosystem forecasts as a result of climate change, although it could also be applied to the oil spill problems that are happening using exactly the same tools around the U.S. And this is something that we're also seeing as something that would be very useful, because with a much smaller domain, you can run with much finer resolution, still using the boundary conditions from the global scale, and come up with a finer scale, more realistic simulations, in this case of the U.S. East Coast, including the Gulf of Mexico. So I'd like to leave you with just a couple of thoughts. First is an emphasis that MOM6 is an open development model. It is freely available, and we strongly encourage people to contribute back. This is managed by a worldwide now group with 7 major hubs and partners, each with slightly different emphasis, and each of which is able to say, if there's a contribution that's causing problems, stop, it doesn't come in. So everything is accepted onto the main branch by consensus. Every institution involved is basically responsible for the regression testing to make sure that none of their key applications are being impacted, along with a whole set of common self-consistency tests. And the point of all this is to encourage new people to be willing to contribute without the fear that they're going to break something. We want this to be a growing community of contributors as well as users, and this is something that we're very much encouraging. I am absolutely delighted to hear about the great work that Paulo is doing with MOM6. And just as a summary, this is the base based on a broad, diverse, and growing community. We strongly encourage partners from anybody using the model to contribute back in the context of the open development spirit of MOM6. In particular, I would strongly encourage our Brazilian partners who are listening today, if you're finding something that you think works better than what's there, contribute it back. Somebody else will take a look at it, improve on it, come back. That's how we all get better together. So thank you very much. I appreciate the time, and hopefully this has kind of given you slightly a broader prospect and a longer term prospect of how we can tackle these important issues together.
Thank you, Robert. That was a great presentation. Really, really interesting. I would like to ask my colleagues here if there are any questions addressed to Robert. If not, we are closing now the topic of oil and entering the Sargassum issue. And for that, I would call on Joaquin. He's already here with us. Hi, Joaquin. I'm going to give you the presentation mode.
Thank you.
Yes, you may have it now.
Window, Brazil, share, and start. Can you see the slides?
Yes.
Perfect. Okay, my name is Joaquin Trinanes. And this presentation will focus on the work that we are doing on Sargassum. This is a problem that has become more relevant in the last years. And the reason is because of the large impacts on the economy, social impacts, environmental impacts, of having large amounts of Sargassum reaching the shore, affecting areas, large areas in the Caribbean, in the Gulf of Mexico, in the north coast of Brazil, West Africa, and the southeast of the United States. So this is a work that is being carried out at the Atlantic Oceanographic and Meteorological Laboratory in Miami, and it involves the Coast Watch Caribbean Gulf of Mexico Regional Node, Atlantic Ocean Watch, and also the Physical Oceanography Division at AOML. I work as the operations manager for the Caribbean, for the Coast Watch node and for the Ocean Watch node. And this is a program that depends on NOAA NSDIS. And the main purpose of this program is to provide easy access to remote sensing products. And the applications are multiple. We develop different products, usually based on the feedback from users, from people having problems and not finding the appropriate, the right satellite products. And so I will focus on the Sargassum problem that we are facing since year 2011 in the Caribbean. Usually we think about Sargassum as a good thing. How good is for environment? It provides a habitat for many different species, but and also in the United States is protected as an essential fish habitat in the South Atlantic US. But in year 2011 something happened, and a very large influx of Sargassum entered into the Caribbean, and generated a lot of problems with the tourism, with the economy in general, and removing the Sargassum usually require millions of dollars. And there are also problems with public health, as for example, they accumulate arsenium and other heavy metals, and so there are different types of problems related to Sargassum. I think that today it can be considered a hub, a harmful algal bloom, and you can see in the image some of the effects of Sargassum once that it reaches the beach. Well, there are here is a quick glossary of some of the sensors that we are using in order to detect Sargassum. MODIS is a historical sensor that allow us to generate large time series in the past, but probably in few months that data will not be available anymore. But we have other sensors that can replace MODIS. At this moment, we are generating Sargassum-related fields from MODIS, from BIRS, from OLI, from Olkey at 300-meter resolution, and from MSI on Sentinel-2 products at 10-meter resolution. The difference in resolution is really, really large, but also there are differences in for example, the revisit time. If we want data at 10-meter resolution, we usually need to wait for 5 days in order to have another pass covering the area, and that's depending on the cloud cover. So usually the sensor working at mesoscale scale usually provide data that is really useful for mesoscale applications in order to have a general view of the distribution of Sargassum in the ocean. We need to be able to monitor and track Sargassum, and the response to this need is to use satellites. There are many data sources, and we can here apply different technologies like in the fields of big data, machine learning, cloud, and distributed processing, data integration, geographic information systems. Using these resources is we can study the drivers behind the Sargassum reaching the shore, and we need to be able to explain where the Sargassum comes from, and to be able to analyze the impacts of Sargassum on the shore. As you see in the image on the right, we can use satellites in order to know about the spatial and temporal distribution of Sargassum. You can see over there, for example, in one colors that there is an area in the north that is the Sargassum, the traditional location of Sargassum, that's the Sargassum Sea. But in the south, you see what is called the Great Sargassum Belt that started forming in 2011. There are some possible explanations for this. Usually, some people say it's not a negative phase of the North Atlantic Oscillation. There are some hypotheses that focus on the Amazon River, Orinoco River, the amount of nutrients, the upwelling in West Africa, the dust from the Sahara Desert. So there are different hypotheses, and we need to work more on in order to find the reasons. And here we can see some of the satellite products that we generate. We are generating what is the alternative floating algae index, that is a measure developed by Chuan-Min Hu at USF. And we're generating this indicator for Sargassum using MODIS and BIRS, a total of 4 satellites, because MODIS is present in 2 satellites, and BIRS in this sensor also in 2 satellites, now 3, there is a new one. And so we cover the tropical Atlantic region and the Caribbean, Gulf of Mexico, West Africa, and well, our purpose is to be able to generate in near real time those fields and be able to use them in order to track Sargassum and to develop value-added products from these satellite data streams that we use. As you see, MODIS and BIRS allow us to have daily coverage. To reach daily coverage. With Olkey, usually we have full coverage every 2 days, and with MSI every 5 days, but usually in the coastal areas. Having the data from multiple satellites allow us to improve very much the coverage. We can see on the top the difference between using a single sensor or combining the fields from different sensors. So we can reach a better coverage integrating the data from the different sensors. But we can also use the collocated data in order to compare the different algorithms. For example, the bottom of the slide, you can see The 10-meter fields to the left, on the left, in the middle, 300 meters, 1 kilometer, and 750 meters. And so we can work with these collocated satellite fields in order to evaluate the density of the Sargassum aggregations and also the size of the Sargassum aggregations. If we are decision makers, we need higher level products. We need to be able to forecast the distribution of Sargassum, and somehow we should know what are the trajectories of Sargassum depending on currents, on winds, and other effects. So the Physical Oceanography Division at UML deployed as an experiment in order to evaluate the effect of winds and currents on different types of synthetic drifters. They deploy these synthetic drifters, and we use that information in order to be able to forecast or to be able to predict the trajectories of Sargassum. And these synthetic drifters, they have a GPS that allows us to know the location. And well, this can be a step forward in order to know better, for example, where the inundation, Sargassum inundation, will take place, and how much biomass will reach the shore. But a problem here is to know, for example, the currents, to know the winds in a regional scale, because usually global models don't perform too well in a regional scales. So there are also this is an area where we should improve. So a few months ago, we organized an event, a satellite activity within the framework of the UN Ocean Decay. The objective of this season was to present the different data sources and the techniques that allow us to know, for example, the geographical distribution and the temporal variation of Sargassum, and evaluate the potential Sargassum inundation level. In this satellite activity, there were 8 presentations and one demo. There were participants from multiple backgrounds and institutions. For example, the University of Miami, the Universidad Autónoma de México, Florida International University, universities of South Florida. So there were around 100 participants, more than a lot of participants, and this activity allows us to confirm the growing interest that Sargassum monitoring has. Well, in order to generate value-added products based on satellite data, we create what is called the Sargassum inundation reports. As inputs, we use the flooding density fields that are being estimated at the University of South Florida. We are also generating those fields internally at OML. They are not operational this time, but we expect to have them operational in short time, combining additional satellites, not only relying on MODIS or BIRS, but having MODIS, BIRS, all together in order to generate those fields. So so from these bulletins, for example, we can extract a lot of useful information that allows, for example, to know the risk for per location or per region, and also to generate time series showing the evolution of the risk with time. Having data from high resolution satellites also impact very much has a positive impact on these Sargassum inundation reports, because it provides an additional coverage, increasing coverage in the coastal area. We are also ingesting and serving data in situ Sargassum observations of Sargassum, here including pictures. Basically, we have a centralized database where we combine in situ observation from different projects. For example, we collect data from the EPICOLLECT 5 Sargassum Watch project led by the University, Florida International University. We also have our own survey at NOAA that allows users to submit observations of Sargassum that we can use in order to validate our Sargassum inundation reports. So one thing I would like to highlight in this presentation is the importance of having interoperable tools in order to be able to visualize and distribute the data. So this is essential because this allows users to access the data within their work environments without worrying about the formats on the remote systems. So we also provide a viewer, what is called Ocean Viewer, that can be adapted to multiple purposes, and also in order to provide to visualize and to provide access to Sargassum products. And for example, this viewer is being used to support hurricane field operations and many other users. So we also include metadata that allow users to find, to search for the products they are interested in. So this is an example showing, well, we provide the middleware where the satellite products, in situ data, models, model data are available. So we can access all of them, and we can integrate them, for example, using Ocean Viewer. We provide them in multiple formats. You can download the data in SCDF, in CSV, HDF, many different MATLAB files. And so you can see, for example, on the left, an image that has been created showing currents, economic exclusive zones, drifters, Sargassum in situ observations, all of them together into a single image. And we can do more things. And for example, and the data is available in near real time. For example, did you see the image on the lower right? You can see some linear features in that is the northern Brazil coast. And this image is from yesterday. It's an image that comes from Olki, but Modis Terra also showed the same features. Well, we are tracking this. We have no confirmation that this Sargassum, but probably is it depicts an area with a very large concentration of chlorophyll. So this is yesterday's image. Probably now in our server we have today's image, and somehow it will give us an idea of how those features are moving and the evolution of them. So here is some of the things that we are doing. We are focusing now on improving the Sargassum inundation risk fields, improving the modeling of trajectories. We want to incorporate satellite new sensors with higher resolution. We need to enhance the data on currents, on winds, waves in the coastal area. So there are areas for improvement. There are also some gaps regarding the growth and decay of Sargassum, the information about the growth and decay of Sargassum. And also we are applying machine learning techniques in order to delineate the Sargassum maps show that we detect using satellites, because that allows us to, for example, use that information to be incorporated into trajectory models. And finally, here is a short summary. We need tools and information in order to take good decisions. So we need to apply new technologies and and approaches that, in our case, for example, align pretty well with the NOAA strategies in science and technology, focus on artificial intelligence, unmanned systems, cloud, omics, data integration, citizen science. Those are areas that we touch within this project. And of course, stakeholder engagement stakeholder participation is fundamental, is essential, because with that feedback we can improve our products and develop collaborative partnerships. And that's all. This is the last slide. Here is the contact info, and you can see there a list of collaborators and partners at different institutions, and some links that maybe you can find useful. Well, thank you for giving me the opportunity to show our work. Thanks.
Thank you, Joaquin. That was great. Great presentation. I would like now to open the floor for an open debate, and you can all raise your hands and ask general questions or towards any of the presenters today. I would like to raise myself some questions just to kick off. I think this topic of having data-driven application is very important, and all of you at some point presented the benefits of having all the imagery that are freely of access and they're built on models that are on open codes, and I think that enables a lot of collaboration and an up-to-date improvement of those systems. But I was just wondering what is on the other side, what is that we could be doing to put in the same playing level field the training for all these countries, if you look into the Americas continent, and the capacity development that we need, not only to the specialists such as yourselves, but to the policymakers or to the youth, the early career ones that are coming. In Brazil, we know we are in a shortage of those professionals and Paulo can say with much better proficiency than myself. We lack much more people being specialists on remote sensing, and especially on those areas of ocean. And I mean, we have so much powerful technology in place. You were doing such a fantastic work, but we need to bring more people on board, both from the policy level and from the newcomers, from the postgrad students. So I would like to understand how you were doing that in either NOAA or in cooperation with the other units and universities. That's one thing. And in terms of the data-driven applications, if you have made any example or anything that you could refer to that is really user-friendly, that could be used by a common citizen just to play around, or for a policymaker that is an environmental authority but probably not directly related to, let's say, Sargassum or oil spill, but is approaching the issue. So just a few questions, but feel free to respond as you prefer.
So if I could weigh in here, I think that we saw a couple of examples, both in Paulo's talk and Joaquin's, of how we get citizen engagement. I mean, people are walking around with cameras, they can report in real time. And once people are saying, oh, I can report this oil spill, they get engaged. They know that something is going on. They can do something about it. Once they get engaged, they start to get a little bit more interested. They want to read more. I think that's a wonderful, you know, even setting aside the value of the, you know, the characterization from the purpose of detection, crowdsourcing the detection, I think that's a fantastic outreach approach. And I if I were wearing a hat, I would take it off to both of you for incorporating that as a way of getting engagement in a very natural way. And especially, you know, people go to the beach, you say, why is this thing on the beach? It's a perfect opportunity, and I think that is a wonderful example of one way we can get people involved. Once you start getting them involved, then they sometimes will take the next step and get a little bit more involved. They'll maybe take some classes. Unfortunately, some of the things we're doing are pretty technically sophisticated, and so you need students who have taken some classes before they're able to kind of engage at the next level. But I think that first step is absolutely critical.
Absolutely.
I fully agree. I fully agree. The citizen science part is essential, and we're trying to enhance that part, interacting with some stakeholders. That's essential in order, for example, to detect problems with our products. And allow us to, for example, to create test beds. We have no problems on somehow creating different test beds for different regions in order to show how well the algorithm and how well our methodologies work. And there are many other applications that, for example, people working with marine protected areas where they want to know, okay, what is the effect of sargassum, or what is the effect of chlorophyll, temperature, and all the variables that, and that information is essential for. That feedback is essential because we have all the parameters, but we can create a dashboard, for example, showing the status of the marine protected area by ourselves, but we are not the users. So if we develop a dashboard without the user feedback, probably it will be a failure. So we need to, talk and discuss and enhance collaboration and somehow both parts should interact a lot.
Absolutely.
And it will be good for both of us. Yeah.
Joaquin, Robert, absolutely. You see how the social media developed. How Facebook or Twitter or this thing, people like to be there. They want to show they are there. They're friends. And we talk much about policymakers, but policymakers also have kids and neighbors, and they walk and they get rainfall in their heads. So the science is social science, engaging people and people finding fun in taking a picture of something on the beach, and then there where we can help have an intelligent response back. It's not just a picture. Wow, you see what I got from my cellular phone? Something that never before anybody saw. I saw it, and show your friend, and the kids start playing like we all learned playing. So ludic, the ludic part of learning, I think this is it is not a distraction. It's a core science. So Rob, imagine taking all the things that MON 6 does and translate that back to kids. So I think, but then we have homework to do. And this is what we are trying to do with the SISMON on the beach thing, that people can actually get engaged and say, oh, I got 3. I said, I got 5. Anyway, that's it.
Yeah, you were talking, I was just thinking about my 3 small kids that I have and how they would actually be so amused to having a gamification experience out of the models that you're presenting, and how they would play around, and that would be maybe a defining path on their career choices in the future. So I think that's something that should be as an outreach and extension work for all this work. But one other thing that I would like to ask and pick your brain on is, I know in Brazil we have been using the powerful technology of imagery to build a whole public policy system for forestry and land use, and that's been very strong, and that's actually the technology that enabled us to really curb deforestation at an impressive rate in the recent past. But when we look and we turn to the ocean, we are not quite there. We don't have a framework of policy for ocean use or ocean security that is so reliant on this technique. And I just wonder, maybe Paulo can bring on some more, but I don't know what is that the matter of the certainty of the science that comes out of the imagery that from ocean is probably more hard to tell, but why we were so effective to respond to the imagery technique on forest and land use, and we cannot develop at the same pace for ocean.
I see. Karen, in 2010, we had a Brazilian SBPC meeting in Natal about the oceans. And one thing that we realized that we always we give our back to the ocean. When the people from Europe came, they crossed the Atlantic, and when they were at the beach, so the ocean was past, so it was not present in our social notion of nation. The ocean is dangerous. There are monsters in the bottom of that. So I'm kidding, but not so much. So I think that we are not there. First, we are land people. We walk on forests and streets, but we are at the beach. So the beach is it's amazing how thin is the beach line. When you look at a map, it has no dimension in millimeters, nanometers. But how many things happen there? So I think we need to focus our attention to develop this ability to engage fishermen, tourism, people that are there having fun, what they saw, in a consequential way, that they will understand. And I give you an example. Cellular phones these days, they measure pressure. So if we just got pressure measurements from all cellular phones, we would know right away how wrong our forecast is, right now, right here. And that is something. So, but you mean, it is not something to be done as a distraction. We need to enwrap this as part of our research, and be able to assimilate data, but more than big, assimilate smile. Let us try to assimilate a smile. When people get the thing and say, "Whoa, I like this product." That NOAA has a buoys with cameras along the shore that people, when they go surfing, I remember seeing this long ago, that they could see the state of the sea. It's a service for a very small fraction of people. Not everybody surf. But I mean, developing in wrapping this ability that the ocean is part of our lives and it is fun. I think that is the way I would suggest that we can go forward.
Yes, please go ahead. I only see your initials, JR Garcia. Is it Jorge Aragão? Is it? No. Okay.
Roberto, are you seeing? Okay. Are you seeing me?
Not yet.
Not yet. Maybe some issue with my camera here. Okay. Okay. Hello, everyone. My name is Roberto Garcia. I work with Dr. Paulo Nobre at SISMON. It's a pleasure. And now I have a question to Matthew about how much do you know, Matthew, about the MARPOL violation? Are they allowed to wash their tanks somewhere in the ocean or near or far the shore? Do you know something about it?
To be honest, I don't know about that. Yeah, we just know bilge jump is a MARPOL violation, and I mean, anytime we see that, that's something that we're gonna not like. But yeah, I'm not sure totally about where you can empty your tanks and stuff like that.
Okay, so we need to do our homework and see this document.
Yeah, I'm sure it's out there. I need to look for it too.
Yes, I've already saw it. Another question is, what to do once you detect the oil in the ocean? Is there any attitude to mitigate the impact on the shore?
So for us in our branch, what we're really interested in is just seeing it in the satellite, outlining that, giving a graphical representation in our product, and then sending that out to the users that can respond right away on the ground and other ways. So yeah, what we do is really just monitor satellites and then send out the information once we get it.
Okay, thank you. Karen, I have a question for you. Yeah, we are talking about social media, about those photos we need to mine in the social media. You don't think is there a way to do some kind of partnership with social media providers? Because we can't use our own account to do it, because if we search too deep, they block our account. That is an ordinary account in those social medias. Do you think it's possible to have some kind of partnership with them?
Yeah, I think it is possible. We can explore, and actually we need to be more savvy on the way we send the message and what we write on the message, because sometimes it's intelligible to you, experts, but out of the room, it gets really hard to understand. So what is it that I'm reading? What should I be doing now? And I think if we need to work on the communication side of it, but I mean, it's possible to have, and we need to train more communication officers so they are able to assist us in the job of translating science. I think that's more effective than actually having the media, but we can work on that. The MCTI media and other medias that can be actually related directly to the project, to the SISMON project. I think that's totally doable. But that's the thing of coming back as to being more, to deploying more systems that are user-friendly, that ordinary people can play around and understand, and they can have an real-time information so that they can disseminate it, and it can get and reach out and make pressure where it needs to be done in the political system. I think that's the functioning of the whole thing, and that's how we can take the most out of the power of this technology, that it's amazing. You know, government reacts well to disasters, and that's the sad story. So we had the major oil spill. So we are here taking a huge investment in oil detection and modeling. If it wasn't for the spill, we wouldn't be here probably, right? And I'm not hoping for another one, but that's when we had the major landslide in Rio de Janeiro in 2011. That what actually made the government to build the system, the alert system that we have nowadays for precipitation and landslide. We didn't have it before. So now we have all we need to actually put the oil monitoring in the medias and in place, I think, because we're still being hit so hard by the oil spill that it's the right time.
Okay, thank you.
We have a question from Milton Campbell. I invited him to join us in the room, but I actually, it's here in your chat. So if you could comment, let me see if he got in, so he could say his question. Yeah. Milton works at INPE, the National Space Institute, as well.
So part of what Milton is highlighting is the importance of making sure that as students get involved, that there are reasonable career pathways for them. And I think that's always a problem, that all of us live in situations where the budgetary pressures kind of come in bursts, and then things dry up and bursts. And it is something where, as you're developing the capability of students, it would be nice. I mean, we're not talking an enormous part of the economy here, the pool of people working on these problems, but to kind of make sure that we have kind of a steady pathway that we can take talented people as they get involved, as they get engaged, and give them a reasonable prospect of, not necessarily a terribly lucrative career. I have yet to find a rich oceanographer, but something where you can make a meaningful contribution over time, and at the same time contribute back to perhaps the communities you came from. Milton, you're here. You can make the point yourself that I was trying to agree with.
Yeah, Milton is also discussing with us another endeavor that we may start soon, that is using remote sensing to map landfills, illegal landfills in Brazil. And we are trying to move on with that challenge. But again, early steps, isn't it, Milton?
Your mic is on. Yeah.
Thank you, Karen, for the invitation. I did a few comments. I was really much enjoying all the presentations here. Congrats for this initiative here. But maybe, I don't know, what Karen also called her attention was that during Joaquin Trinanes was showing some very recent imagery of the north coast of Brazil. I'd like just to maybe raise the possibility of, instead of being Sargassum, those features are more like cyanobacterial blooms, such as trichodesmium. And you have seen from satellite monitoring observation that maybe this type of blooms, they have been increasing. Of course, the capacity of satellite observation has increased so much in the last years. So that maybe there is a bias in it, but we don't know about all the climate changes and gases and so on. Maybe those, as you probably know, maybe there is something going on. So besides the Sargassum thing, which is increasing the last years, is a big issue, in French Guiana as well, and sometimes also arriving in the Amapá and the Pará coasts somehow. And also being as false alarms for oil slick monitoring as well. So we have a lot of challenges. And of course, you do need to keep our capacity building efforts. But I'll take the opportunity to raise that what we do with the people that you already formed there. So they're living in the US and Europe and finding good jobs, good positions. And I'm so happy to see that the effort we've been doing here is being useful and has a reasonable standard to find a job in such competing markets. However, we lose the brains. So we definitely need to be aware of the importance of the ocean for different reasons. And I'm quite sure that you all are very much aware of that. And you need to change this picture. And if you do not take the opportunity of the decade for the oceans, it will never happen. So thank you very much for your attention.
Just one comment. I agree that probably it's not Sargassum. We have seen this before. And usually you see a very large, bloom that lasts few days and disappears. And the behavior is absolutely different from Sargassum. So probably it's not Sargassum. But what we are measuring is the large concentrations of chlorophyll. So it's coherent. It probably can be cyanobacteria.
Thanks, Milton. I agree with everything that you said. It is a major concern on how we keep those brains and actually how we keep them within the government, because all the agencies need those specialists, and we haven't actually managed to retrieve them well and to keep them here, because also it's not competitive for most of them to be here. But that's definitely an issue that we need to solve urgently, or our environmental policies will never stand. Sammy is raising her hand. Sammy?
Thank you, Karen. And thank you all so much for the wonderful presentations and the really informative discussion. I'm sorry to insert myself. I have to run to another meeting, but before I do so, I wanted to ask if I could quickly take a picture, a group shot, and perhaps those who don't have their cameras on, including anyone in the audience who'd like to turn your camera on, please go ahead and do so. I'll give you a couple of seconds while I set up my screenshots. Excellent.
She's our official photographer.
I know there are a few more folks. Dorida, Emily, Gustavo. Excellent. Thanks. Okay, great. 1 second. Just take a test shot, and we'll take one more. 1, 2, and 3. Perfect. Thank you all so much. And I'm sorry to run, but it was really wonderful to join all of you. And thank you so much, Karen, for moderating today. I'll see you tomorrow.
See you tomorrow. Yes, I would like to thank you and pass it on for concluding remarks. I mean, I'm not in a rush, so please feel free to add other comments. And for those who need to leave, remember we have more tomorrow. Yeah, I think, Robert, you wanted to mention something? Or you were just waving your bye-bye?
I was just saying it.
Oh, okay.
I was just bidding adieu to folks here on what I think has been a very interesting discussion and with really remarkable capabilities that I think are coming together. I think one of the things that strike me is how much more integrated our communities have become. That observations and modeling, remote observations and in situ observations, crowdsourcing, it's something that really is quite revolutionary in even just the past 10 years. When I think back on what was available during Deepwater Horizon 12 years ago, we have a much more tightly integrated system involving a lot of people from the public in ways that we didn't have 10 years ago and certainly didn't have 20 or 30 years ago. And that's I think, a very important and valuable trend where we no longer, for instance, describe ourselves as, say, an ocean modeler or a theorist or an observationalist. We're just working on the problem, and you're using all the tools, and we're increasingly trying to make it so that you don't have to be a specialist to make use of the various aspects of the tools, and you can, the science that emerges from this synergistic approach is one that I think benefits tremendously. Models are great for what they are, but they need the observations to tell you what's happening on the ground. The observations on the ground need the models or the theory to kind of synthesize into what a local observation means in a bigger picture. And I think we saw some wonderful examples of that today.
If I may, Karen, thank you, Robert. Absolutely, I think my discovery, I think our discovery, is the power of us, that we work together beyond borders. That we can win a war, but what is the war that is fought about the climate change? That is not an enemy. That's not a gun. That was the war of knowledge. So in wrapping and bringing people and working together, and I would tell you, Robert, the GFDL, NOAA in general, approach to make tools available for others to collaborate and develop together. And I think this is, and along what you said, Karen, danger moves us. Biologically, we have either we move or the thing eats us. We have to run. So we must run together in a coordinated fashion. And it is very, very, very good that we are doing this now. We are having this conversation, but we will not stop with the system here closed. We will keep working together. And that is the most important thing. And thank you very much. Thank you for the opportunity to be with you all here.
Thank you all. This was a great day and definitely a very valuable source of sharing knowledge and incentivating not only early careers, but whoever's interested in joining the ocean effort and the ocean decade that is ahead. The technology is so powerful, but the people behind it is even more. So that's the difference, right? And only hoping that next time we have a woman presenting, not only men.
Good.
See you tomorrow. Thank you so much for your time. Bye.
Bye.